Hello, everyone, and welcome to the Weekly Space Hangout for Friday, October 28th, 2016. I'm Fraser, Cain, publisher of Universe Today. This week, we got a bunch of cool stories for you. We're going to be talking about, dark energy totally overturned this week. So there's that. We're also going to be talking about a cool young star system caught in formation. We're going to be talking about habitable worlds around red dwarf stars that might be water worlds. So joining us this week, we've got a bunch of guests. Oh, we've got them all right here. Special guests. I'm going to start with Kimberly Cartier. Kimberly, welcome.
Hello, Fraser. Hello, viewers. Go Cubs!
We got Morgan Renberg. Morgan.
Football's better than baseball.
Oh.
Blasphemy.
Oh, it's all just sports ball to me, guys. Paul Metzger.
You and me is going to have work.
Shame.
Shame. Yeah, you'll get your chance to shame the astrophysics community in a second here. Don't worry. You have to wait about 20 minutes, and then we'll get on it. And we've got a special guest. We've got Derrick Pitts. Welcome to the Weekly Space Hangout.
Thank you very much. Hi, everybody. And I'm sure that one day in this century, the Phillies or the Eagles will actually get to a championship.
Is it like hockey, but like with a different kind of ball? I don't understand this thing. So before we get on with the special guest, I just want to do a little bit of housekeeping. The first thing is I want to remind you that this is an interactive live show, and so if you want to chat with the other fans of space itself as well, just make sure you watch these shows live. We do them every Friday at noon Pacific, and if you just go to the Universe Today channel, you can find it out. The second thing that I would like to remind you is that a lot of people watch this show as a podcast on iTunes, and if you are doing that right now, if you're not watching it live, but you're actually listening to it on your headphones while you're out for a walk, take a second and give us a rating on iTunes. It would mean a lot to us, and it would help more people find the show. So if you want to know how you can give back to the community, the best thing you could do, really, I can imagine, is to give us a nice, good rating on iTunes for the Weekly Space Hangout. So thanks a lot. Let's get on with the show. So Derrick, why don't you let people know who you are, what you do, and we'll get on to the science.
Sure. Thanks, Fraser. Hey again, everybody. Derrick Pitts. I'm the Chief Astronomer and Planetarium Programs Director at the Franklin Institute Science Museum in Philadelphia, Pennsylvania. Franklin Institute is one of those big hands-on science museums. We're the oldest hands-on science museum in the country. The planetarium we have here is the second oldest planetarium in the United States, preceded only by the Adler Planetarium in Chicago. Up on our rooftop, we have a rooftop observatory with a roll-off roof that currently has 3 Celestron 8 reflectors and a 10-inch Zeiss refractor, vintage 1931, 1932. It's a really great instrument, and used to be paired with a 24-inch Fecker reflector telescope on the roof, but a few years ago, I took it out because there was just too much city light for an open cage telescope like that to work. And so we do all kinds of public astronomy programs. You name the type of astronomy program, we do it here at Franklin Institute. I also write and produce planetarium shows and have a planetarium show currently in circulation around the world called To Space and Back. Yeah, it is really cool.
And so you, I guess, do quite a bunch of, like, we have that in, I don't live in a city anymore, but we used to have a great planetarium in Vancouver. It's the same thing. There was like a bunch of telescopes set up that you could go, and they'd have open observing nights so people can come down and see what's in the night sky this week.
Yes. The way we do it is our observatory is open every day. The sky is clear. So we do a lot of solar observing, and have been actually since the early 1930s. The Franklin Institute opened on this spot where we are in Philadelphia in 1934, January 1st of 1934. The museum had been around since 1824, but when we opened at this new spot, that's when we opened with the planetarium and the observatory. So we started doing public observing daily, looking at the sun, first with just white light filters, and then we added hydrogen filters to look at flares and prominences back in the early 1980s. And we do that all the time. And then once a month, we have a program we call Night Skies at the Observatory, which is open to the general public to come in and take a look at whatever we have to observe through our telescopes. Now, here's the interesting thing about this, actually, Fraser, is that here in Center City, Philadelphia, we are right smack downtown, Center City, Philadelphia. You can't get any more Center City than that. So if you know what that means our observing targets for the evening are the moon.
Yeah, Jupiter maybe. Yeah.
Now, we have all the bright planets, all the bright stars, things like that. Not much in the way of dark sky. But the most interesting thing is, for as long as I've been doing this, the number I guess off the top of my head is about 80% of people that come to our observatory have not looked through a telescope before. It just blows my mind.
Yeah,
And,
absolutely.
People have not had so much experience. On one hand, I find it really dismaying. On the other hand, I'm really happy because it keeps me in a job. So,
yeah, I get that experience too, right? When you give people a chance to see Saturn for the first time with their own eyeballs, they can't just conceive that what they're seeing, because it has the shape, it has the ball, it has the rings, and it's real, it's live. They can see the bright star in the sky, and then they're looking through the telescope and they're really seeing it. So like that is just got to be from to take a person from I'm kind of interested in this stuff to being a fan. It's got to be that step is just amazing.
Yeah, it really is. And that's the thing that we all live for at the telescope is the aha moment when people get it. And I always describe it this way: when people actually are seeing something through the telescope for the first time, they're seeing it because you hear them go, oh, and then they've seen it.
Yeah.
So,
as opposed to I can see the Cassini gap there. Okay.
Right. There's one other way I use that moment, though, and that's particularly with Jupiter. And I'm sure a lot of listeners have maybe thought about it this way or used it this way also, but it started in 2010, looking at Jupiter. And I would say to people, so now you've seen Jupiter. So I want you to think about this in a way that Galileo may have thought about this when he suddenly realized he's the first person ever in history to see this planet. Imagine what he must have felt like. And then realize that you seeing it just now for the first time yourself, that's your own discovery moment. That's almost as valid as Galileo's first observation. That sort of helps it sink into people's brains what they've seen.
But it must be difficult to get across to people just how much the light pollution is really obscuring their view of the cosmos around them. That, anytime I'm in a big city, I can only make out a few of the brightest stars, and that's pretty much it. And where I live, we've got the Milky Way at night, and so it's night and day.
Yeah, it's an enormous challenge. So thank goodness we have the planetarium that we couple with these observing programs to help give people some idea of what the real sky looks like. And then we work hard, actually, Fraser, to get people to recall their viewing experiences of dark sky. Typically, a good half of the audience, maybe a little bit more, has had some dark sky experience someplace. So we ask them to, dredge up that memory and try to compare that with what they see here in the city, and then help them understand that if they were to get themselves away from the city again, they could see so much more.
And so when you're not sending people out to look in the telescopes and not designing the planetarium shows, you also do work in astrobiology and helping inspire people to get into that field. So could you let me know a little more about that?
Sure. Yeah. I'm sure many of the folks that you talk to, or if you haven't, I'm one of those guys that's a NASA Solar System Ambassador. So, that we do work on behalf of NASA, helping people understand what kind of research is taking place in the solar system using NASA resources and things like that. So you can think of me also as an astrobiology ambassador in the same way in which I use NASA resources to help people understand how exciting astrobiology can be, particularly as a higher education career choice at the graduate level and beyond. And so I do this across the board, but I also have been specializing in doing this for historically Black colleges and universities, where awareness of astrobiology, I should say that awareness about astrobiology as a career choice is universally not as well understood as it could be. So I try to do what I can to help get people excited about it, especially considering it's not that you're coming at it necessarily through astronomy, but it could be biology, chemistry, engineering, mathematics, physics. You could come at this from, lots of different entry points and make a serious contribution. So I'm doing a little bit of work on that side.
So what aspect of astrobiology do you find is sort of the most interesting, kind of exciting one for people to go into these days?
Extremophiles.
Yeah.
Yeah, extremophiles, because, we think about looking for life somewhere else around the universe. And this, how this first started out, Fraser, was like 20 or 30, 40 years ago. People were looking for life somewhere else on the other side of the universe. And slowly it's been coming closer and closer and closer. And so now we're looking for life right here in our own backyard, on the planets and moons of our solar system, right? But when we start to examine our own environments here on this planet, we find that the environments here can be so unbelievably wild, and still we find life there existing somehow. And I am just blown away understanding that there are creatures living in the deepest portions of our oceans. There are creatures that live inside solid rock. There are creatures that live in lakes buried under miles of ice in Antarctica. All of those kinds of crazy environments, and lots more that I didn't even mention, have this one common thing, that somehow life has figured out how to do that. So then you start looking at the moons around the solar system, and you look at those and you think, hey, wait a minute. It's an ocean of liquid, quote unquote, water, close enough. Couldn't there be something down there? Oh, I love it.
Yeah, absolutely. And the places that they're finding liquid water now is just more and more and more. Now we think all the large Jovian moons, several of the moons of Saturn, maybe even places like Pluto, like further and further out there, that there's other mechanisms that are creating this liquid water, that it could be everywhere. It is really pretty amazing. Where do you think, if we do find life, where do you think that first discovery is going to get made? Do you think we're going to find it on because although we just lost the Schiaparelli lander just last week, the orbiter made it, and it's going to really help us get to the bottom of that methane mystery. But there's also, who knows what's going on with Mars with other rovers. There's what's happening with Enceladus, with Europa. Where do you think is going to be the place we'll turn up life first?
Okay, so we're going to rule out intelligent life on Earth. Okay, right? And we'll move on from there. I'm thinking, and then we can. I'm really wondering what Martian cows look like, that there could be so much methane in the atmosphere that's being detected there.
They're very small, very small cows. Yeah,
very small. Okay, great. But the places I'm really interested in are the Jovian moons. The moons of the outer planets of the solar system. I think those are going to be really intriguing places where wouldn't it be great to start out saying, look, here's a place where we're going to find some life in existence. I'm really betting more on finding much more complex chemical compounds that might be building blocks leading to life, rather than necessarily finding full-blown forms crawling around on the ocean floors. I'd be stunned and amazed and happy as can be, but I'm sort of backing up toward a simpler level of entry point. They've been around as long as the Earth has been around. Yes. Are the conditions the same as Earth? Not really. So I'm gonna back up and say I'm looking for the building blocks. If we can find more complex ones, that's great. For Mars, though, I really would like to identify some fossils there, that life did exist at one time. I always advocate sending some geologists, some paleontologists, a few biologists on the first expedition, let them fight it out for a couple of weeks, and then a few months later, we'd have some real evidence that there had been life on Mars.
Yeah, absolutely. So I'd like to talk about sort of more of your education outreach. What do you find is sort of like your way to get people to consider astronomy and research as a career, and sort of what resources do you make available to sort of help people begin that journey?
Well, so there are always those that are that self-select out into this, So
Yeah.
Those are easy pickings. That's the low-hanging fruit. But to really engage other people, you have to find an entry point that works for them. And since people can come at any particular topic from whatever angle works for them, I work really hard to find out what angle would work best for them. Some are interested in the physics, some are interested in the mathematics, some are interested in the chemistry. I've had success working with people around geology, planetary geology in the past. That's worked out well. But to engage people's imagination about what is going on out in the universe in any one of those regions, and helping people understand how it's possible for the universe to manifest various kinds of phenomena that simply aren't possible to be created here on Earth because of the conditions we live in, and how that opens the door to a vast number of possibilities for wild phenomena. That does a great job in getting people engaged, because they can use their own imagination to find something that's really exciting and interesting to them. Space exploration, in and of itself, is making a big difference these days. I had a chance to speak to a group of students out in Reno, Nevada, at the University of Nevada, Reno special magnet school for kids. And we talked about life in the solar system for a bit. And then we talked a little bit about traveling to Mars, because it was not long after Elon Musk's presentation at the International Aerospace Conference
in Mexico. Yeah.
Yeah. So I cut right to the chase, and I said to them, so, given all this kind of stuff that we've heard a little bit of excitement about recently, how many of you would be willing to make a trip to Mars? There's about 100 kids in the room. More than 90% of them raised their hands and said they would go. And I further explained, some more of the difficulties, and not many more hands went down.
Wow.
So I find that, all of the recent films that have been out, whether we've liked them or not, Gravity, Interstellar, The Martian, all of these have gone a long way to sort of reignite people's interest in exploring the universe again, whether it's in person or sitting in an armchair, hunting for supernovae through Galaxy Zoo or something.
Yeah, and I think some of the work, people have gone both, into, say, computer science, or learn how to work with computers, and then they find they can take that technical ability and connect it to their love of astronomy and do work in that way. And they can also sort of go the other way as well, which is start out as an astronomer, but then realize that it depends on a lot of computers, depends on a lot of mathematics or other physics, and find their way into that other career as well. It's just it's about working with your brain and about solving problems and engaging with the kinds of sort of mysteries that are in the world that are, as more people need to be able to do that.
Yeah, you raise a really interesting point there, Fraser. Something that was really driven home to me when I spent some time in Chile last summer at a lot of the radio observatories and optical observatories through the ambassadors in Chile education ambassadors program. And one of the things I really learned, that really hammered home, I should say, is that 90% of the jobs, 90% of the work that goes on in these facilities is not research astronomy. 10% is research astronomy. But the rest of the pyramid is built up of people from all across every kind of industry you can think of. And so here at down at the ALMA facility in South America, they have 66 12-meter dishes, radio dishes, spread out across a huge amount of land up at 16,500 feet. And in order to do work on those telescopes, what they do is they hot swap them out. They have a special truck that they drive from the operations center at 10,000 feet. They drive that up to 16,000 feet. They pick the telescope up, the whole telescope, with this special truck. They keep it hot. In other words, they keep it running, essentially. The telescope is always cooled to about 4 Kelvin. So they bring it down the mountain to the repair facility, do the work there, and take it back up. Well, there's a whole crew of people who take care of this very special truck that moves the radio telescopes. And so when I talked to the guy about how he got into this, he said, I love working here. It's really great. It's so exciting. How did you get into this? Well, I was a heavy equipment operator, and this job came in. I'm thinking, wow. So somebody that's into whatever it is you think you're interested in, there's an angle for you to get into astronomy through. And like you said, it's about using your brain, about using imagination, using your skills.
Yeah, I get emails all the time from people who are like, I've loved astronomy since I was a child, but I went into computers and now I'm a database administrator. I wish I could get involved. And I'm like, I could get you right away names of people who are begging you to search, through some of these big databases to help them dig up information that, this is the thing they need the most, is to be able to get access to a database administrator, which would be amazing. I got a couple of questions coming from the people who are watching. So one, this comes from Arjun, and asking about, is there a dark sky in Pennsylvania? What's your closest dark sky? Does it even exist there? I mean, I see the dark sky finder, and it's like your whole area is just this bright yellow blob. But
yeah, right. So the deal is that on the eastern side of Pennsylvania, Philadelphia is right here on the border. It's across the rivers, New Jersey, and that's the I-95 corridor right there between New York and Washington, D.C. That area is completely awash with light. There's no question about it. There are little holes and pockets over in central New Jersey in the Pine Barrens, down in the southern portion of the state, inland from the coast and things like that. Over here in Pennsylvania, as soon as you start to get outside of Philadelphia and go north and west, things begin to darken immediately, because there are only two other large cities in Pennsylvania between Philadelphia and Pittsburgh. I should say three. There's State College, that's up north, central Pennsylvania. Then there's Harrisburg, that's almost down toward the southern border, and a little bit below that is York. But other than that, Pennsylvania is incredibly rural. So there happens to be one of the best dark sky sites in the United States is in north central Pennsylvania, right on the Pennsylvania border. It's called Cherry Springs State Park. Dark, 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 and dark.
What's the time frame? If you hopped in the car, how long does it take you to get there?
5 hours. 5.5 hours.
Yeah. Yeah.
It's really worth the drive. And the park is set up specifically for amateur astronomers. They have the power kiosks right out in the parking area. You can't use, your headlights at night. You can't use laser pointers, the whole 9 yards.
That sounds great. Yeah.
It's a good spot.
Yeah. And then one other question here. This one comes from old Jorgen Nordhagen. So what is your guess of how long before we find life outside Earth? What do you think? Place your bets.
Ooh.
We won't hold you to this.
Yeah, so I'd love to be optimistic and say that something's going to happen within the next 10 years. I think the reality is that the 10 years indicates that we're talking about something that's within a pretty close distance, to Earth. And that means it's a solar system discovery, right? Because anything else is simply too far away. So,
yeah.
when I think something like this might happen, I'm thinking 50 years, seems to me to be more reasonable, unless somebody's sending a signal to us.
Right.
But us actually finding it, the scale of the universe is really far more enormous than we can imagine, and that really, drives a lot of that.
Well, it was absolutely an honor and a pleasure to talk to you today. So, can let people know where they can find out more if they're in the city. Stop by, check out the observatory. What's the deal?
Absolutely, sure. The Franklin Institute. You can find us on the web at www.fi.edu. We're on the Benjamin Franklin Parkway here in the city, not far from the Philadelphia Museum of Art, which is one of the best art museums in the country. We have a number of other great museums right here on the Parkway. It's a great part of the city to be in. You can always contact me. My email address is dpitts@fi.edu. My Twitter handle is @CoolAstronomer, and I'm always willing to chat with people. We invite you to come down and partake of all the great stuff we have here, including the observatory and the planetarium. We have great shows, and we show you a really fabulous view of the sun and show you what your star looks like in ways you never could have imagined it before.
Fantastic. Well, I will absolutely check it out next time I am in that wonderful city. So thanks a lot for joining us on the Space Hangout.
Thanks for having me.
And thanks for working with everyone and inspiring them to keep looking up.
Sure. Thanks.
All right. Take care.
See ya.
Okay, so now we're going to move on with the episode that we've got so far today. Who do we want to talk to? Actually, first I want to remind you, if you're watching this, that this is, of course, a live show. Go ahead and ask any questions that you might have. We don't have a lot of stories today, so I think we will have some time to talk about them as we go. So that's a opportunity. But you can go ahead and just use the live chat in YouTube to do that there. You can also... if you see, there's this chat down at the bottom of the screen. This is, of course, the Slack community that we've set up for you. So if you want to join us over there, someone will probably put some instructions in the YouTube channel, explain how you can join the Slack channel. And I figured it out. It's the Slack channel that when a person joins, that it messes up the listing. So that's what's causing it. All right, I'm going to start with Paul Metzetter because I gotta know what's driving Paul so crazy this week, and I want to know what he did to what happened with dark energy.
Yeah, so I've been pulling my hair out all week, as you can see. There was a paper that was actually submitted over a year ago, but it was finally accepted just last week, where the authors this is a story where there's so many things going wrong, I don't even know where to start. For one thing, there's the results of the paper, which we can talk about. And then there's what the authors of the paper are kind of adding in, both in the paper and in the press release, as commentary on top of those results. And then there's what the media, various publishing outfits, journalists, and writers are taking from the paper itself and from what the authors are saying. So you go essentially from a paper where just the results say dark energy basically exists to headlines that say maybe dark energy doesn't exist at all and this Nobel Prize winning discovery has been wrong the whole time.
Okay, so now when I sat down at a science conference and talked to Perlmutter, he told me that. Oh, did I lose you guys? Okay, there we go. He said, here's how we did it, which was that they looked for supernova candidates. They found all these supernovae out in the universe. They measured the distance of these things over time, and they got a sense that the expansion of the universe was accelerating. Mm-hmm. Was he lying to me?
Saul Perlmutter is not a liar. Well, maybe he is in his personal life, but professionally he is not. He's a stand-up guy.
Yeah.
So in 1998, we've known for a long time that the universe is expanding, but in 1998 it was discovered by accident, not quite by accident. The interesting story between these supernova searches is they were assuming that the universe was actually decelerating. So they're actually looking for a slowdown in the universe, but they found something of the right magnitude, but the sign was wrong. And there were two independent groups that were doing this at the same time, using different telescopes, using different supernova targets, using different methodologies, the whole deal. And they were both arriving to the same conclusion at the same time. And the initial emails between the groups, they're saying, hey, we think we screwed something up because we're seeing an accelerating universe. What are we doing wrong? And then the other group responded with, hey, we were just about to tell you the exact same thing.
Right.
So we weren't even looking for an accelerated universe, and we happened to find one. And that was in 1998. And you're right, that was using supernova data. Essentially, supernova are dimmer than they ought to be. And we can track this dimming of supernova as a function of distance. And this tells us very directly that the expansion of the universe is accelerating. Right. So what this recent paper does is analyze a larger set of supernova, uses a slightly different analysis method. There's all sorts of messy, sciencey stuff you have to do in terms of data analysis and methodology. And they find an accelerating universe in this very recent paper. They find an accelerating universe with a 3 sigma significance, which is pretty high. I'd take it. I would celebrate a 3 sigma result personally, but it's not the standard we typically like in physics. We like having a 5 sigma or even higher significance.
Yeah, no Higgs boson unless there's a 6 sigma.
Right, something like that. So the analysis of the paper finds a universe or points to a universe with dark energy. The layer that the authors themselves are adding onto that is it's only a 3 sigma detection, so therefore dark energy probably doesn't exist. The accelerated expansion is just a fiction. It's not really in the data. We're making it up, and there you go. And that spurred all the media headlines saying, this Nobel Prize winning discovery, this fundamental pillar of modern cosmology is wrong after all.
Right. So if I understand correctly, let me see if I can just sort of summarize this, right? That originally the measurements were done by 2 separate groups. They achieved a certain level of accuracy. Another group I think it was out of Oxford, right, did another survey, got less accuracy, significance, and said, well, since we weren't able to find we did a larger survey, but we got less accuracy or less significance, therefore it's not real. But that's not
pretty much.
But that's not true, because it's just because they got less significance. I guess that's, but isn't also like the supernova survey is just one way of detecting dark energy?
Yeah,
and
that's the big thing is the accelerated expansion was discovered almost 20 years ago. And cosmologists and scientists are not idle people. We like to stay busy. And we've actually found multiple independent lines of evidence that all point to a universe with dark energy. And that's kind of a key point that's like missing from a lot of these stories is modern science. When we have a pillar of modern science, it doesn't matter the field, that pillar never comes from just one line of evidence. It comes from multiple ones, all working independently with their own shortcomings, their own strengths, constraining different parts of the picture. They all point to the same thing. So even if we're at the point now in 2016 where you could just toss out the entire supernova data set, just say, screw it, I'm sick of supernova, they're too many, I'm going to ignore every single supernova, I'm not even going to use that, we still have overwhelming evidence for the existence of dark energy.
Yeah, like the observations from Planck and WMAP alone provide the level of accuracy that you require for that detection of dark energy, right?
Right. We have the cosmic microwave background with Planck and WMAP. We have observations of the large-scale structure of the universe. We have things that we don't even talk about to the general public, like the integrated Sachs-Wolf effect. We have this size and shape and structure of cosmic voids. We have just like this ridiculous pile of information that all point to dark energy, all independently, because that's really important. So yeah, for a while, we've actually kind of known that supernova probably aren't going to be the strongest constraint of dark energy that we have. So when we look ahead over the next 10 or 20 years of where more information about dark energy is going to come from, it's actually going to come from other probes. Supernova are a little bit messier than we would prefer in terms of measuring dark energy. So we've actually known that for a long time. And so this paper, if you take out the strong claims or the ridiculous claims, it's an interesting kind of nuts and bolts paper, like, how well can we use supernova to constrain dark energy?
Not well.
But that's not even close.
Right.
Yeah. Well, it's still pretty well. 3 sigma from one supernova data set. There's another supernova data set that these authors didn't use. And so I wondered what their analysis method would get coming from that. And also keep in mind, these authors, just based on the way they're writing the introduction to the paper, their conclusions, their statements in the press, they think accelerated expansion is a fiction, that we've been fooling ourselves for 20 years. And so from the most pessimistic position possible. Like someone coming out with an angle that I'm going to set out to disprove the existence of dark energy, they still get a 3 sigma detection.
Now, do you want to rail? One thing, your camera's jiggling, so I'm not sure what you're doing.
Oh yeah, because I'm sitting on a bed and I'm getting really energetic.
Okay, that's fine. Would you like to now take a pound of flesh from my astronomy journalist, industry?
Yeah, so there's several levels of shame here that need to be applied. Shame to the authors for having this weird axe to grind. Shame to the University of Oxford for writing like a really horrible press release. And then shame to the science journalists that are just copying and pasting this press release when they could have called up any astrophysicist. It doesn't even have to be me. It could be any of them. And we would have all given you at least another perspective, some general commentary that you could toss in there and say, you know what, I still sleep at night thinking that dark energy is a thing.
Yeah, and in fact, that was my instinct. So we actually didn't run it all in Universe Today this week. I saw the story come out, and I'm like, wait a minute. What? Yeah.
In any science journalist, when you read a press release and the authors, even quotes in the press release, are saying, oh, a major pillar of modern scientific understanding is shaky, or just take it with a grain of salt. Just call someone else up.
Yeah. So, dark energy survives, and in fact, dark matter went through the same thing, like literally last week as well. And it was the exact same, a very similar thing, which was like people had done, and I actually talked about it in the episode last week, and I took a little flack, which is just like this idea that the galaxies are able to rotate on their own without needing to have some halo of dark matter surrounding them, without flying apart. Therefore, dark matter isn't real. But just like with dark energy, there are plenty of independent lines that support dark matter that have nothing to do with the rotational rates of galaxies. So once again, someone with an axe to grind about dark matter is sort of supporting perhaps a competing theory, right?
The exact same situation. You could, let's just ignore all rotation curves. Like, just toss it out. We still have overwhelming evidence for the existence of dark matter.
Yeah. Well, fantastic, Paul. I will take that back to my the other people in my industry and see what I can do to kind of tune them up. So I'm glad your eyes have stopped rolling like a little bit now.
Right. Now I need a nap.
It's nap time. Okay.
It's nap time.
Okay, so now we're going to move on. We're going to talk to Kimberly. Let's talk about a young star system that was caught breaking up.
Yeah. So I have to say this is one of those images where I saw it pop up on my news feed, and I saw this image, and it just sort of blew me away with how spectacular it was. This is an image from the ALMA and VLA. So ALMA, the Atacama millimeter submillimeter array, large millimeter submillimeter array, and the very large array, both radio-ish telescopes, who are observing a star-forming region in the constellation Perseus, and saw, to their great surprise, that there was what appeared to be a single disk of star-forming, planet-forming material that actually had 3 protostars embedded within it.
I'm actually got the picture right beside you right now on the screen. So
yeah, so the thing is that most stars in the sky are actually in multi-star systems where there's actually 2, 3, or 4 stars that are all gravitationally bound together. And up to this point, we've only ever observed one type of formation mechanism for these multi-star systems, which is where you have a large cloud of gas and dust that's slowly collapsing and fragments into individual stars, some of which are closer to each other and so start gravitationally interacting. But that formation mechanism alone can't explain all of the different configurations and dynamics that we see in multi-star systems. especially when you have 2 or 3 stars that are actually very close together. That's hard to form when you're going from a large scale and trying to bring them closer together. It's hard to get them to stabilize that way. And so for a while, astronomers have theorized that there must be some sort of other formation mechanism, possibly through a disk that's already collapsed by angular momentum and then fragments after that because of gravitational instability. And lo and behold, we have just observed the first system that we've seen forming with this disk fragmentation instead of cloud fragmentation. So this is another one of those theories where we've sort of known that it has to be there this whole time, but this is the first piece of observational evidence that these multi-star systems actually do form this way.
And
so I just saw it and it blew my mind.
The picture, and I pretty much left the picture up beside you for the whole conversation. Just this.
It's so great.
Yeah, this disk of material, and you can see the binary companions in the middle, and then this third star.
So you see the 2 binary ones.
Yeah, that's going
which
around.
are only about 63 astronomical units apart, and then that third one on the outside is less than 200 astronomical units apart. So this is an incredibly tight 3-star system. Yeah, and once all of the extra material gets accreted either onto the stars or maybe a planetary system if they're really lucky, what will happen is the 2 stars in the middle will have a very tight orbit, and they'll just be spiraling around each other with that third star orbiting around both of them.
And I'm not sure sort of what the distance of the stars are, but maybe you could get planets either orbiting the whole system or just orbiting the center stars. I guess I'm not sure what the mass difference is between them, but yeah.
So I don't think we know about the masses yet. I would imagine they'd be somewhere around a solar mass or a little bit smaller maybe, just because some of the material might not accrete. But if there's going to be planets, I imagine it would be more likely around the outer star as opposed to the 2 inner stars where there's a bit more gravitational instability. And so it would be more difficult to form planets in a more unstable environment. So I would imagine if there will be planets in a few more thousand years, they'd be around the outer one. And keep in mind this whole system is only 150,000 years old.
Right.
So they still have a while to go before it finishes forming and maybe starts forming some planets. So a few thousand years from now, maybe we could check again.
It's pretty interesting, though, how long it's taken to turn up images of star formation, multi-star formation like this, because that's the rule, right? Not the exception. Most of the systems in the Milky Way are these multi-star systems. So it's kind of, we've seen a lot of planetary systems forming. It's kind of surprising that we haven't seen more of these multiple star systems coming together like this.
Well, I mean, also keep in mind, this system is pretty far away. It's 750 light years away. And we've just not really had the power to see these sorts of things on this scale for a while. This is, like I said, this is an incredibly close triple star system that from side to side is 200 AU, and it's very far away. So until we had things as powerful as ALMA and VLA, we probably wouldn't have detected these. Plus, the actual process of formation happens so quickly on the scale of the star's lifetime that there's just, statistically speaking, it doesn't last very long, and so you're not going to see many of them.
Right. Phenomenal. I was like you, when I saw this, I was just so excited. It was such a beautiful
I just sort of stared at it for about half an hour being like, oh my gosh, I can't believe we're actually witnessing this incredible process.
Yeah, absolutely. Fantastic. Okay, Morgan, let's talk about what we've got this week.
Yeah, not only are most stars out there in the Milky Way double stars, they're mostly all small stars too, what we'd call dwarf stars. And that includes the star around which we found this planet that we've been talking about a lot recently, Proxima Centauri. This is what we'd call an M dwarf. It's one of the smaller kinds of stars that you can have. And despite the fact that they're numerically dominant in the galaxy, we haven't spent that much time thinking about how planets might form around them. There's probably more planets around M dwarfs than any other type of star in the galaxy, But because we care a lot about Earth-like planets around sun-like stars, and the sun is not a dwarf star, we've put a lot of effort into modeling the formation of planets around more typical stars. And so this work that came out this week was aiming to add some detail to our understanding of how stars and how planets form around small stars. And what they did is they randomly generated a whole population of these small stars. And around each one, they randomly placed a bunch of planet cores, so the rocky sort of cores that form into planets inside the disk. And then they populated that disk with gas and dust and all the other stuff that goes into making a planet. And they basically ran time forward on all of these at the same time. And what they found out was that actually around an M dwarf, you'd expect to find planets most likely around the size of Earth. And that matches up pretty well with what we think we've seen around Proxima Centauri b. But the more striking result was that many, perhaps most of these planets would be what we call water worlds. We typically call a planet a water world if it has, say, more than 10% of its mass in water, and some of them have as much as 50% of their mass in water. And that's tremendously more than the Earth has. So, we always say surface of the Earth is covered 70% by water. By mass, that water makes up just 0.02% of the mass of the Earth. And yet we have all of these oceans. And so if you add a water world, you're talking about no land and tremendous depths of water. And although we usually talk about water as being one of the most important things for forming life, and we use that sort of in our basic filter when we're looking for habitable worlds, we say you have to have liquid water. Having too much liquid water might actually be worse for life than not having enough. Because it's really important, obviously, to form life that you have more than just water. And if your planet is 50% water, or even 10% water, it's going to severely dilute anything else that might be in that water. And so here on Earth, for example, we think that the boundary between the rock underneath the ocean and the ocean layer might have been really important. That might not have been where life formed, but you have a lot of chemical processes that go on at rock-water boundaries that produce more complicated molecules that can then eventually go into life. But if you have a water world, the sort of percent of water that's in contact with the rock at the bottom of the ocean is very, very small in comparison to, say, the percent of rock under Earth's ocean that's in contact with the water. And so you'd be producing relatively little of these important molecules, and then you'd be diluting them in a much, much larger volume of water. And so it's telling us that this very dominant population of planets in the galaxy might look at first blush as a good place to find life. They can be in the habitable zone, they can be Earth-sized, they can have water. But if we look more closely, we might start to find that many of them aren't great candidates for life after all.
But I guess, a lot of the downsides of being close to a red dwarf star that's in that, in that flare star stage of its existence, a lot of those downsides might be sort of protected if you were on a water world, right? If you're a couple of kilometers down on, beneath the ocean on this planet, you're not going to worry about the high levels of radiation that are pouring out of the star. You could even, if you're, I don't know if you're necessarily tidally locked, but maybe if your planet is tidally locked, it may remove some of the downsides of being tidally locked to the star. So it sounds like there could be some advantages to being on one of these sort of worlds that are mostly covered in water as opposed to ones with more distinct land masses.
Well, this is an area of research that needs a lot more development. Like I said, because Earth-like planets around sun-like stars aren't typically thought of as being water worlds, we haven't really investigated chemically or physically what would happen in these sorts of environments. But if these are the dominant collection of planets in the galaxy, then certainly we want to invest a lot more work into trying to understand that.
Yeah. Super interesting. It's funny, 10 years ago maybe when you talked about the planets around red dwarf stars, they weren't even on the radar of exoplanet researchers. I don't know where Kimberly can speak to that, but they're awful places. Nobody wants to be there. You don't want to be near a red dwarf star. Forget it. Let's go look for sun-like stars. But it turns out they're easy to find, and that now with a lot of the worlds that are getting turned up are sort of the right size that we would expect. So it's sort of like a pretty fascinating area to go into. And now I think it's almost like the astrobiologists are catching up with the exoplanet discoverers. They're finding these worlds, and the astrobiologists are kind of going like, I wonder if it would be all right for life, and then sort of follow up from there. So as you said, more research necessary. With Proxima Centauri, we've talked about this before, there couldn't be a closer world. So now's our chance. Let's build a really great observatory, something that's almost custom built to analyze the planet or maybe planets at Proxima Centauri and try and get to the bottom of this work. Fantastic. Kimberly, you, I think, had some interesting news that you were going to talk about sort of just at the end, if we had any time at the end of the show. And we do have a little time at the end of the show, right?
Yeah, sure. So I actually just got back from an observing trip down at the Green Bank Observatory, which, if you don't know, is a very large radio telescope. They have the Green Bank telescope down there. It is second only to Arecibo and soon to the third to the Chinese radio telescope. It's an amazing facility, and I just spent the week down there as a part of a collaboration between us at Penn State and the group looking at Voyage's star, which is also known as the Alien Megastructure Star. And we were collaborating with the Breakthrough Listen project, which is run out of Berkeley SETI. And so we actually pointed the Green Bank radio telescope at Voyage's star late Wednesday night, and we're trying to get a comprehensive radio spectrum of Voyage's star from 1 to 100 gigahertz. And we're analyzing these data in every single way we could possibly think of to see if there is some sort of signal there. So that's what I've been doing all week. It's a pretty exciting time.
Remember, if you're interested in the alien megastructure, we've got Kimberly here. We will bring you the news first. Just stay tuned to the Weekly Space Hangout. You don't need any other news sources. We can give you the straight goods. That's exciting that you got access to that telescope and you got to be able to collaborate with some radio astronomers on this.
Mm-hmm. Yeah, one of the really cool things we did is part of the lots of we have to calibrate the radio telescope in every single band in lots of different ways. But one of the cool things we did was we actually also pointed the Green Bank telescope at Mars, which has a ton of extraterrestrial equipment around it. Things like the Mars Reconnaissance Orbiter and MAVEN, and there's the rovers on the surface and everything. And we pointed the radio telescope at Mars to see if we could actually pick up any of the radio signals coming from this non-Earth technology that's sitting over there at Mars. And we actually did see a signal from Mars. We don't know which of the pieces of equipment it came from, but it was sort of a proof of concept that if there is technology around a world other than Earth, we are capable of detecting it. Kind of cool.
That's really cool. So, but still no real specific information about the actual details of it. You don't know if it's an
I mean, the volume of data we have to go through to actually analyze and see if there is a signal is just absolutely staggering. There is at the end of this is going to be nearly a petabyte of radio data that we have to go through. So there's definitely not going to be any results in the near future, but hopefully sometime in the next year we'll be able to take a look really closely at every single frequency we can think of.
Fantastic.
Yeah.
Cool. All right. Well, I think we're sort of reached the end of this week's episode of the Weekly Space Hangout. Thanks, as always, to everybody who joined us to watch live. And thanks to Derrick, who was our special guest. I would like to give our regulars here a chance to let people know where they can find out more. So let's start with you, Kimberly. Where do people find out more?
People can find out more, as always, by following me on Twitter at AstroKimCartier, and I've been giving some updates on our radio observations of Voyage's star all week. You can also check out my website at www.kimberlycartier.org.
Fantastic. Paul Metzutter, where do people find out more?
Shame.
Shame. Where will they go to receive their shame?
You can visit my website, pmsutter.com. That has links to all my shows and activities. I also host another podcast called Ask a Spaceman, where if you enjoyed my rant on this show, you can get more of the same delivered right to your ear. And you can also follow me on Twitter and Facebook. I'm at Paul Matt Sutter. And if you really enjoy rants, you can pay me to do even more. Patreon.com/pmsutter.
Whew, I'm glad you did it so that I didn't have to. Morgan Renberg, where do we find out more?
Yeah, well, this week you can check out my latest YouTube video over on SciShare Space, where we check out the physics behind why some planets are rocky and others are gassy. Otherwise, you can follow me on Twitter at Morgan Renberg or visit my website, morganrenberg.com.
Fantastic. I'm going to push everyone into the gallery view. There we go. The Brady Bunch view of us here. Cool. And of course, I saw people talking in the chat, especially you, Erie PA dude, which is that we are experimenting with a new design of the show. And of course, it's based on the logo, the original Weekly Space Hangout logo. Big thanks to Sean, who's been working with the show to give us a new design. I would love to know your feedback. So I'm running this show solo, and I was switching cameras. I was turning on lower thirds, and we were checking out pictures, and it was pretty cool. So, but I'd love to know any specific advice that you have on how we can make this better. So just please let me know what we can do to make this better. I know the sort of the borders are a little wide, like it's too much not video and more just Saturn. And who needs to see that stupid planet? So I would love to know any more sort of advice and suggestions and feedback that you have. Go ahead, if you want, just put it in the chat, give me an idea, or go ahead and drop me an email, and we're constantly tweaking and improving it. So thanks for letting us know. And I want to, as well, now we've reached the end of the show, and even though at the beginning of the show I said you should go to iTunes and leave us a positive comment, you just kept running, you didn't do it. I understand. But now you've reached the end of the show, you've been sitting in the car or, waiting to just hear the last little bit, and then you're going to go inside and make dinner. Go to iTunes and give us a kind review. 5 stars would be great. And then that way we can get more people to find out about this show, and they can get their space news this way, as opposed to the other shameful people who perhaps are going to tell them that dark energy doesn't exist.
Shame.
Shame. Oh. Cool. Well, thanks everyone for watching this week. Thanks to the panelists and our special guest for joining us. And if you haven't already, click subscribe wherever. This is my universal do a thing. It feels a little threatening, doesn't it? I'm pointing at the screen. Go ahead and subscribe to this channel and the Twitter handles of all the people who joined us this week. All right, thanks everyone. We'll see you all later. Bye.
Bye.